Okay, so we're going to take a look at kinetics post lab. So the first thing is we're going to discuss the role of S2O3 2 minus in the reaction. So it's really important to recognize that this kind of happens, this reaction happens in two parts, and you should have discussed this in lab, where essentially you have all of the reactants, which is going to be your I minus plus your bromate plus your acid, and it's going to produce a handful of things. But most importantly, what it produces is iodine. It's not balanced at all. You can look from your reaction. This is reaction one. It produces iodine. That iodine is then consumed by another present reaction. S2O3 takes any iodine that is created and forms I minus. That's the second reaction. So essentially, what happens is these three things react to give you I2. That I2 then reacts with the S2O3 to give you I minus. Well, we've got more I minus here. That I minus creates more here, and the reaction keeps going, producing I2. So this is kind of a cyclical thing where it produces I2, the I2 gets consumed, and it gets returned. And that keeps happening until the S2O3 disappears. Once the S2O3 is gone, then the iodine forms. The iodine plus the starch, when there's enough iodine, those two things form a complex, and that forms that blue color. So that's really what the reaction is doing. And we're going to discuss this again, but it's really important that you understand how this reaction runs. One is going, two is going. Once the S2O3, that stops and it just produces iodine. So why the S2O3? Well, one thing that we're going to notice, it is the same quantity for all reactions. Every single reaction has 10 mils of this sodium thiosulfate. It's Na2SO, Na2S2O3. Again, we don't really care about the sodium part of it. S2O3 2 minus, and it's the same quantity. So it is constant throughout. So it is constant, and therefore the once all of that's gone, that's when the blue color disappears. So the same quantity, that's constant. So really what it's used for is it's used to track the reaction, track the speed. So a reaction speed, um, and the faster that it's consumed, the faster the blue color forms, and that's why we use it. The other reason for this is if it was just reaction one, you'd produce iodine pretty quickly, and then the blue color would appear. What S2O3 does is it kind of acts like a fuse. We need that S2O3 to go away in order to produce the I2. So it kind of allows this reaction kind of delays the addition, the creation of that blue color. So ultimately, what happens is that delay of consumption of the S2O3 leads to a longer time frame, because if this was just reaction one, this would happen way too quickly for us to time with a stopwatch. So we use the S2O3 to kind of delay the start of our stopwatch to the end of it. So that's the other reason that we do it. So the delay of the consumption of the S2O3 essentially delays the consumption and really the production of I2 to form the starch complex. All right. So consider this reaction. So this is some generic reaction where we have some mixture, mixture one in this case. Propose a set of volumes. Propose a set of volumes for mixture two. Okay, that would enable you to determine the order with respect to D minus. So all I really care about is with respect to D minus, comparing the reaction times of reaction one, mixture one, and our new mixture. So we're going to create this new mixture. So with respect to D minus means we want to change D minus and we don't want to change anything else. So the easiest thing to do is we want to, let's say, double the concentration of D minus. That's actually pretty simple to do if you just double the volume of it. So if we double the concentration of D minus by going with 40 mils of the D minus mixture, um, we've added 20 mils of D minus means we need to lose 20 mils of something else. And water is not involved in the reaction. And we have to reduce to 20 mils of water. And everything else is going to remain the same. So D minus goes to 40, the water goes to 20. These two remain constant. We still have the same volume, but because we've doubled the volume of D minus, but we haven't changed the total final volume, it's still, we're going to have twice as much D minus, and that is going to allow us to prepare those two things. All right. So if the reaction was first order with respect to D minus, okay, so we're going to say first with respect to D minus, and the reaction time of mixture one is 60 seconds. So first order with respect to D minus, that means that if I double the reaction rate, so 2x D minus should lead to a 2x of the rate. That's how the first order process, right? So rate is equal to K rate D minus or D minus. There we go. So doubling D minus will double the rate. So if I doubled the D minus, okay, so if I doubled the concentration of that, I should double the rate. So how fast is that? So be careful here. We're not doubling the time. We're actually having the time. So it's not going to take 120 seconds. It's going to take 30 seconds to actually form. So we expect that to happen in 30 seconds or half the time. So doubling the rate means going twice as fast. Twice as fast means it's going to take half of the amount of time. So just don't get caught up in that. Don't get caught up in doubling everything. Just keep in mind what that means. When double rate means twice as fast. All right. Describe three experimental conditions that cause the reaction mixture to turn blue more quickly. Okay, so we're speeding up the reaction ultimately. That's really ultimately what we're doing is we're just increasing the rate of the reaction. To do it quickly, for each condition, identify whether it impacts the magnitude of K, activation energy, or both. So if we are if we are going to increase the reaction rate, there's three things that we can do. We can increase the concentration. Okay, so increasing concentration. What this is going to do is it's going to cause more collisions because there's more molecules that have the potential to potentially react. So increasing concentration, that will make the blue color happen more quickly. So increasing the concentration. Will that affect anything? Well, K is locked in. Okay, so K is locked in at its value. So we do not expect K. K is temperature dependent. So we don't expect to see any change for concentration. K is K. Okay. Activation energy is locked into the mechanism involved. So actually, neither of these is expected to be affected by concentration. Okay. So that's what we're stuck with. So K is temperature dependent, and activation energy is essentially going to be mechanism dependent. Okay. All right. So increasing concentration should actually affect neither of those. Increasing the temperature. Increasing the temperature will actually make things move faster. Increasing the temperature causes an increase in energy and an increase in the number of collisions. Both of these are going to increase the rate of the reaction. This will affect K. So K, because the temperature is changing, K will increase, or K will, yeah, increase. But activation energy will not. And then the final thing, the addition of a catalyst. This will change the mechanism completely. So it's going to change the route at which in all of those things that go with it. So because it's a completely new reaction, because it's completely new route, K and activation energy will change. K is going to change somewhat because it's a new root, but activation energy is generally going to decrease. It should decrease activation energy, but it will change the magnitude of K. That is all going to depend. K may be bigger or smaller, but it's all going to be dependent on what else is involved in the reaction. So adding a catalyst will affect both. All right. So now let's move on to the problems. So these are a little bit more um, mathematical. And here we go. So we're going to kind of do all of these together. So we have this reaction above. Okay. And with this reaction above, we've done 3 experiments. Okay. Identify the order of each reactant with respect to mercury chloride or mercury HgCl2 and the oxalate ion in the overall. So before we even proceed, we are going to go with the generic rate law for this reaction. Rate is equal to K times the concentration of reactant 1, mercury chloride, raised to some value. We'll just call it X. That's the order of reaction, times the concentration of the oxalate C2O4 2 minus raised to the Y. Okay, so we just need to solve for X and Y, and there we have it. In order to do that, we are going to take these reactions and we're going to kind of look at them in terms of how they compare to one another, and we're going to plug these in. We can actually solve this without doing a whole lot, but I'm going to kind of show you that. So if we look at reaction 2 and 3, okay, notice that we do have a change in mercury, but we don't have a change in oxalate. So any changes in rate are due to the amount of mercury. Okay, so we're going to use, for the first one, mercury chloride, what we're interested in is looking at the rate of, and we always want the bigger numbers on top. So I'm going to put reaction 2 above reaction 3. So I'm going to put reaction 2 above reaction 3. And I'm basically going to plug in all of the numbers for the generic rate law, and I'm going to put them equal to each other. So for reaction 2, I have a rate of 7.1 times 10 to the negative 5 molarity per second. I might ignore units in a little bit. All over reaction 3, which the K value of 3.5 times 10 to the negative 5 molarity per second equals. Now K, so now we're going to write out K times concentration of reaction 2, which is 0.105 raised to the X. I guess that's molar. Raised to the X times concentration of 0.30 raised to the Y. We don't know K yet, so we have to just substitute in, but we're going to find out that it's not going to matter. And then this is for reaction 3, 0.052 raised to the X. Oh, those should all be molar, but I'm going to skip them now. Over 0.30 molar raised to the Y. So looking at this, this is reaction 2 over reaction 3. What we expect for 7.1 over 3.5 times 10 to the negative 5th, that is going to round to about 2. Okay, so it's about 2 for that one. K over K, that, so equals, that rounds to 1 times, or that cancels, K over K is equal to 1. 0.105 over 0.052 turns out to be 2 raised to the X. And then finally, 0.3 to the Y over 0.3 raised to the Y is just simply equal to 1. So we end up with is 2 is equal to 2 raised to the X. X is equal to 1. So we now have our value of X. I can replace this with the value of just 1. Okay, so we can substitute that in and we have our order for mercury. So with respect to mercury, it is going to be first order, excuse me, it is going to be the reaction is first order with respect to HgCl2. All right, good. How about C2O4 2 minus? So if we look at C2O4 2 minus, we can see that reaction 1 and 2 change, and we're going to use reaction 1 and 2. Because 2 is larger than 1, I'm going to put reaction 2 over reaction 1. So reaction 2 over reaction 1, and I'm going to repeat this process. So reaction 2 on top, so 7.1 times 10 to the minus 5 divided by 1.8 times 10 to the minus 5 equals, I've got K over K. Concentration of mercury, 0.105, raised to the, actually now we know it's raised to the 1. It's not going to matter, but we could put that X as well. If you wanted to do this one first, you could have 0.105 raised to the 1, 0.30 raised to the Y, 0.15 raised to the Y. So now we reduce 7.1 divided by 1.8 rounds to 4. K over K is 1. 1.5, 0.105 over 0.105 raised to the first reduces to 1. And finally, 0.3 raised to the Y over 0.15 raised to the Y is going to be 2 raised to the Y. So we end up with 4 is equal to 2 raised to the Y. Y has got to be equal to 2. And so now we can change that and substitute that in. So now we can say that definitively, and it is also second order with respect to the oxalate C2O42 minus. All right. Overall reaction is, we're just going to add those two together, third order. Third order. Second order with respect to C2O4, first order with respect to HgCl2. This is A, solved. All right. So moving on. Calculate the value of rate constant. So we can actually take any of these. So for the calculation of rate constant, I can take and substitute in any. Every single one of these should give me the exact same rate constant. So I'm just going to take reaction 1, and I'm going to plug in these values. So I'm going to take all of those values for reaction 1, mercury, the carbon compound, and the initial rate, and I'm going to plug them in, and I'm going to solve. So off we go. So rate was 1.8 times 10 to the minus 5. Actually, I'm going to rewrite the equation here. So rate is equal to concentration of HgCl2, K times concentration of HgCl2 raised to the 1 times concentration of C2O42 minus squared. And now I'm going to plug in the actual values. Go back to blue here. All right. So my rate for reaction 1 was 1.8. I'm going to give myself some space so I don't run out. 1.8 times 10 to the minus 5 molarity per second is equal to K. Concentration of mercury in this case was 0.105 molar raised to the 1, and concentration of the oxalate 0.15 molar squared. And so now, if we do the math, we solve for K, divide by everything, we end up with, and I'm going to leave some space because I want to do the units for it, K is equal to 7.5 times 10 to the negative 3. That's the numbers. So let's take a look at the units. I have molarity per second on this side equals K times molarity squared. So what we end up with, this side turns into molarity cubed. I'm going to divide both sides by molarity cubed. So I have 1 over molarity cubed. 1 of the molarity cubed goes away, giving me 1 over molarity squared times seconds. So there we go. We have our answer. 7.5 times 10 to the negative 3. You can plug anyone in and you should get the same answer. All right. So the last question is essentially saying, okay, so given these conditions, we know K, we know the orders, calculate the initial rate under these conditions. So we are simply going to take this reaction, now that we know K, and we're going to plug these values in and solve. So here we go. So for C, I'm going to take my rate is equal to K, which we now know, times concentration of HgCl2 squared, or raised to the first, sorry, C2O4 2 minus squared. And now I'm going to plug values in. We are looking for rate. K came out to be 7.5 times 10 to the minus 3, 1 over molarity squared seconds. I'm going to zoom in a little bit. And the question is saying that mercury's new concentration, mercury compound's new computation is 0.020 molar, and oxalate is 0.22 molar squared. Let's deal with, we're going to do the numbers first. We calculate rate to be 7.3 times 10 to the negative 6. Let's deal with units. I have 1 over molarity squared seconds times molarity squared. So molarity squared cancels, and I am left with what we should be left with is we have molarity on the top, seconds on the bottom, molarity per second, which makes sense. A rate should be in molarity per second. There we go. There's the value of molarity per second. So those are those three solved. Let me highlight first order with respect to mercury, second order with respect to C2O4, and overall is third order. Perfect. All right, moving on to the last one. So this is going to use some knowledge from other things. So suppose the reaction mixture, one is carried out at 90 degrees Celsius. Use the Arrhenius equation derived in this week's experiment to calculate the rate constant. So I'm going to use an old one. Please use the one that you guys derived in lab. But the old one I'm going to use is natural log of K is equal to negative 5.90 times 10 to the third times 1 over temperature plus 23.4. There we go. Okay, so again, make sure that you have your own value in there. So I'm going to plug in the temperature. So natural log of K is equal to negative 5.90 times 10 to the third, 1 over the temperature. It was 90 degrees Celsius, which is going to be 363 Kelvin. Really important that that is in Kelvin. Again, we need absolute temperatures. We can't have negative numbers, plus 23.4. And now we do the math. So natural log of K is equal to that first part. You should get negative 16.3. When you divide those, when you divide by 363 Kelvin plus the 23.4. Then we have 7.15 is equal to natural log of K when we do that math. And then finally, K is equal to 1270. And now we have to decide what the units are. So what are the units for this? Because it's a value of K. So again, what we're going to do is, in order to determine the rate law, or the units for K, we can always do the math for it. You don't ever have to kind of memorize this or know this. I know that rate is equal to K times concentration of I minus times concentration of the bromate times concentration of H plus squared. This is what you got probably with your reaction. So this is the equation that this mixture went through. And so this is the rate law for it, the generic rate law, although we did solve for the orders. And so we know that rate is in molarity per second. I am looking for whatever K, whatever units are left. We don't need numbers. We can just solve for these things. Molarity times molarity times molarity squared. So what we end up with is molarity per second is equal to K times molarity to the fourth. I'm going to divide both sides by molarity to the fourth. Divide by molarity to the fourth, or I'm going to multiply by 1 over molarity to the fourth. Those cancel, and what I'm left with is the units for K. K is equal to, cancel out one of those, 1 over molarity to the third times seconds, or we could say molarity to the minus 3 times seconds to the minus 1. Whichever you prefer is totally fine, but we do need units with our K. So molarity to the -3 times seconds to the -1. Here we go. There's our K value. Problem solved. Again, these two were experimental for you. This and also this, they should come out to be close to that, but please use your own experimental information for that one. All right, or I hope you did. All right, using that experimental rate law that we had from part one, actually I wrote it when I was doing the units, and so let's rewrite it. So the rate is equal to K. We do know K now, right? With the calculated K value, so I'm just going to plug that in. 1271 over molarity cubed times seconds. Okay. Times concentration of I minus times concentration of the bromate times concentration of H plus squared. Calculate, we want to predict the rate of the reaction. So I know K already, 1271 over molarity cubed per second or times seconds. My iodine was 2.0 times 10 to the -3 molar for reaction one, right? Reaction one. For part one, yeah. Uh, Bromate was zero point 0.8 or 8 times 10 to the -3 molar. And then finally, 2.0 times 10 to the -2 molar squared. And what we end up with when I multiply all of that out, 8.1 times 10 to the -6. And again, we got to deal with units. 1 over molarity to the third seconds. Molarity, molarity, molarity squared. Molarity cubed gets rid of 3 of those. I've got 1 molarity on top and I've got seconds on the bottom. So we end up with rate is equal to 8.1 times 10 to the -6 molarity per second. Perfect. Okay, problem solved. So the last one, and this one's kind of the most complicated, not really the most complicated, but we're going to kind of recall some of the information that we had. So this comes from your data and calculation section where we determine how much iodine is formed. And so I kind of want to walk through this pretty quickly. So so for this, remember, each reaction has 10 mils of the S2O3 and a 50 mils total. So each reaction, so we want to know how fast this reaction occurs. And you did this for calculating of your times or your rates in your original one, but I just want to walk through it again. So each reaction has 10 mils of the 0.001 molar S2O3. Okay, so with that said, if I have 10 mils of this times fraction, I'm going to multiply by concentration, liters in the bottom, moles in the top. Now, these are not going to cancel out. This is a little bit of a trick. Oh, let me just plug the numbers in first, and then I'll show you the trick. 0.001 moles per 1 liter, right? So 0.001 molar is the concentration. This is the concentration of my S2O3, 2 minus. Well, if I do the same prefix for both, it's going to be the same ratio. So instead of moles per liter, I can say millimoles per milliliter. Now milliliters is going to cancel and it doesn't change concentration. As long as you put the same unit in front and same prefix, it's going to be the same thing. So instead of solving for moles, what you probably did in lab, we're going to solve for millimoles. So if I multiply this out, 1.0 times 10 to the -2 millimoles of S2O3 2 minus. This was consumed for all reactions. So we know that much S2O3 is consumed for every single reaction. So with that in mind, I want to pull up reaction 2. So I2 is going to react with 2 S2O3s, and it is going to turn that back into 2I minus plus S4O6 2 minus. So this is reaction 2. So again, for every S2O3, every 2 S2O3s, I'm going to be consuming 1 iodine. Where did this iodine come from? This came from formed in reaction 1. So our reaction happened, produced I2. The I2 is gobbled up by the S2O3, and that's what we're doing. So I want to figure out if I want to figure out how much iodine was created in the first reaction, I'm doing it indirectly by basically saying, well, S2O3 is reacting with it. So everything S2O3 consumes was produced in the reaction above. So this is an indirect way of figuring out how much I2 was actually formed. So right here, we're going to take that equation and we're going to say, well, if we end up consuming 1.0 times 10 to the negative 2 millimoles of S2O3 for every single reaction, reaction 2 says that, well, if that were true, then I want moles of S2O3 to go away, and I want moles of I2 to remain. And again, for every 1 mole of I2, 2 moles of S2O3 were consumed. And again, I can just simply say millimoles, millimoles. As long as I put the same unit in front, they're the same thing. So 2 millimoles of the millimoles of S2O3 cancels. And what I'm left with is, let's see, 5.0 times 10 to the negative 3 millimoles of I2 is formed. That is how much I2 is formed in reaction 1 before all of the S2O3 is consumed. So with that in mind, we can just simply say that S2O3, um, the S2O3 formed that much, and because it formed that much, we can turn that into a concentration. And so let us do that. Let's need 1 second. Page, there we go. Just need more space. So if I form 5 times 10 to the negative 3 millimoles of I2, well, that was in a total volume of 50 mils. And here I can actually eliminate the milli here, and I've got moles per liter. And this gives me a concentration of 1 times 10 to the negative 4 molar I2. Why is this important? Well, for reaction 1, I am producing, let's go right out reaction 1, 6I minus plus BrO3 minus plus 6H plus yields 3I2 plus the bromide plus 3H2O. This is reaction 1. So what we're seeing is this reaction, the one that we're interested in, the timing, produces I2. And so if we write the rate expression from this, okay, we can see that the rate expression basically says, look, the rate is equal to 1/3 the formation of the change in I2 all over the change in time. So this is going to allow us to figure out the time. This is really what we're looking for the blue to form. Well, the change in I2, we started with nothing because we didn't have any I2 to start. It wasn't part of the reactants. So 0 molar. I guess we should do final minus initial. So minus initial, there was no I2. But initially, we know that we consumed 1 times 10 to the minus 4 molar. Initially, I didn't have any. I know that I ended up consuming this much. We just did that calculation. So we know the overall delta is just simply going to be 1 times 10 to the minus 4 molar. And then the rate, well, we calculated that above in 1b, we calculated that 8.1 times 10 to the minus 6 molarity per second was the rate at which we consumed it. And so now we just plug those two values in and we solve for it. So let me just plug those in. Rate 8.1 times 10 to the minus 6 molar. Molarity per second equals 1/3 times concentration of I2, which happens to be 1 times 10 to the minus 4 molar. all over delta t. Solve for delta t, and you end up with 4.1. Molarity is going to go away and leave behind seconds. So 4.1 seconds is how fast that reaction formed. All right, or how fast the reaction proceeded. Great. All right, good. And that should be that. So that gets through all of those, and that should be good. So if you need more information on this, I'm happy to do another video. Please find me and let me know. But it is a complicated thing. It's a really interesting reaction, but kinetics is difficult. So good luck. If you have any questions, feel free to reach out to me or your professor.